topic called the product rule. We've already seen um, the, the power rule. The power rule, if you recall, power rule. If we were taking the derivative of x to the n, then the derivative would be n times x to the n minus 1. Well, the product rule relies on similar strategies. Having trouble with the r's catching on here. So the product rule will be used in essence when you want to take the derivative of, well, the product of two functions. So for example, 2x times the sine of x. Okay, if you notice there are two functions, you wouldn't necessarily see them with parentheses, but the fact that we're taking one function, we'll call it f, and another function g, and looking for the derivative requires the product rule. So as we've done with everything, we are going to jump into the limit definition for the product rule. Two functions, f and g, are being multiplied as you can take from the example above. So we have the limit as h approaches 0 of f of x plus h times g of x plus h. There's our f of x plus h minus the original function, which is f of x times g of x. And of course, that's all over h. So at this point now, this is where the ingenuity and the real genius of whoever came up with the product rule comes into play. There's really nothing we can combine here because g of x plus h and g of x are not the same term. So somebody came up with this great idea of adding a fancy form of 0. And that fancy form of 0 looks like this, f of x plus h times g of x. Now it's a minus, so we're going to follow it up with a plus, and we're going to add the exact same thing, f of x plus h times g of x. So in essence, we did not change a single thing about this function. We simply added a fancy form of 0. You know, it's very similar to the strategy, that should be a h down there, very similar to the strategy of multiplying by a conjugate where we multiply by a fancy form of 1. Well, the reason this helps us now is because you can see here the limit as h approaches 0. I can pull f of x plus h out of these first two terms right here, and I'm left with g of x plus h minus g of x. And then I can pull a g of x out of this term here. So I pulled f of x plus h out of a difference here, and now plus, I'm going to pull a positive g of x out, and I'm left with f of x plus h minus f of x. And of course, that is all over h. And then we can apply our rules of limits, how we can separate the limit of a fraction into the sum of those two limits. So I'm going to take the limit as h approaches 0 of f of x plus h times g of x plus h minus g of x, and I'm going to put just that piece over h, plus the limit as h approaches 0 of g of x times f of x plus h minus f of x all over h. So those two pieces right there that are over h should look familiar to you. Those are the actual limit definition of a derivative. So if I follow up here and I actually take my limit, I end up with f of x plus 0, which is just f of x. And this is the derivative of g plus, that's just g of x. And that's the limit definition of the derivative of f. So we get the derivative of f of x times g of x is equal to, right there you see it, f g prime plus g f prime. Let's look at a quick example here. The one above, I believe we had, was the derivative. Let's slow down. I'm scooting along here. The derivative of 2x times sine of x. So that's clearly a product of two functions. We'll say the f function is 2x and the g function is sine x. So it stands to reason, if we follow along here, we take the original f of x and the derivative of the second one. Plus, now we take the original second one times the derivative of the first one. So in simplified form, we get 2x cosine x plus 2 sine x, or, depending how fancy you are, if you want to show off a little bit, factor the 2 out, and you get x cosine x plus sine x. And that, my friends, is the product rule for taking derivatives.